Good morning, everyone. So I'm very pleased today to present you our recent development in my group about accelerated MR imaging from shorter data acquisition to faster image reconstruction. So the context of this presentation will be, of course, a high-resolution imaging. In particular, given the high signal-to-noise ratio, we can reach at high magnetic field. And as you can see here in this example, this is the ultimate resolution of 120 micrometer in plane with a slice thickness of 600 micrometer. And so we would like, of course, to collect such kind of data regularly and routinely at neurospin. But of course, the challenge we faced is that acquisition time is really prohibitive, and very likely the subject will move during this kind of exam. So we really have to think about new methodologies to speed up the acquisition and the image reconstruction. So as you know, MRI data are usually collected in the case space and not in the image space, and this is the main reason why MRI is so slow. The data are collected typically line by line, as represented by these red dots, and the image is then reconstructed by just applying an inverse Fourier transform. And compressed sensing is one of the techniques that has been introduced now for more than 1 decade to collect less data without compromising image quality. And compressed sensing relies on 3 complementary pillars. Typically, the sparsity of the image in an appropriate domain. Here I took the examples of the sparsity or compressibility in the wavelet domain. As you can see, the original image can be just represented by a few non-zero coefficients. The second pillar is the way we subsample or downsample the case space. In contrast to parallel imaging that performs a regular and uniform undersampling, compressed sensing relies on the idea of incurrence undersampling, which basically amounts to introducing pseudo random undersampling in an appropriate way. And compressed sensing then relies on the third pillar, which is nonlinear reconstruction. So basically, there is a strong interaction between acquisition and reconstruction in this domain, and that's why in the rest of my presentation, the two will be tightly connected. So compressed sensing has been FDA approved and CE marked in 2017 in the market, and all the MRI vendors have pushed and proposed a new solution, a new product, typically to reduce by a factor of 2 the total exam time. So as you can see, it has been declined for T1 and T2 imaging, but I would say that the reduction by a factor of 2 is pretty disappointing because it's already reachable by parallel imaging techniques like GRAPPA or sense acquisition. So in the rest of this presentation, we will focus mainly on T2 star rated imaging. And I'm going to start by summarizing the sparking methods or algorithm we have proposed in the context of T2 star rated imaging. T2 star is an acquisition setup that allows you to have long echo time. So you traverse the center of case space at a large time points, and also allows you to collect data along pretty long readouts. So in this context, we can really introduce new flexible sampling pattern. And this is what Carol Lazarus has done during her PhD, for which she got significant prizes and awards. And we will see that these kind of techniques may allow us to dramatically speed up the acquisition by factors that are more significant than 2. And to start with, so I'll just remind you some results you have probably already seen in my previous presentation. This was the 2D results we got on the 70 scanner at a resolution of 500 micron in plane, but of course at the expense of thick slices of 3 millimeters. because this was 2D imaging, but sparkling was able to really faithfully approach the image quality we got in the conventional Cartesian sampling shown on the left-hand side, and especially in comparison with the classical undersampling approach related to radial or spiral imaging. Both of them actually suffered from severe artifacts, notably because of the B-note inhomogeneities. But of course, we wanted to go further and to approach high resolution, not only in 2D, but also in 3D in isotropic manner. So how to extend 2D sparkling to the 3D imaging setting? This is this question we're going to face now. So originally, of course, the naive idea to go from 2D to 3D imaging is to rely on stacking in the K-space and stacking 2D sampling patterns either along a cylinder or along a sphere. And this is what we did originally. And we got significantly good results on ex vivo imaging, as shown here in this 3D views on baboon brains at 7 Tesla. But when we decided to collect in vivo data, we actually realized that we faced severe artifacts at highly accelerated regimes. So for that reason, the stacking strategy was limited typically to a factor of 10 and not to 17 as before. So, but we got pretty good results at 600 micron isotropic in comparison with the classical stacking strategy of spiral, which suffer again from B-note inhomogeneities. And we particularly well reconstructed the cerebellum in contrast to what was obtained with stacking of spirals. But as we wanted to go further, we actually need to envisage other solutions. To some point, we could say that the stacking strategy was not optimal in an attempt to really speed up the acquisition, either the cylindrical or the spherical approach. And then we also tried other approaches, like based on a parcellation of the 3D K-space domain, in which we optimize only for a single shot at a time and then fill in the full K-space by just making the shot turning around at a given elevation. But this approach was actually suboptimal because we didn't handle the interaction between the shots. For that reason, we decided to work on global 3D sparkling, in which all the shots and all the samples of a given shots are optimized simultaneously. And this is what I'm going to present right now. And this work has been done by Ciuciu GR in my group. So actually, we fully redesigned the original sparkling algorithm, not only to work on 2D, but to work on 3D, from a target sampling distribution, from which here you can see only a projection in 2D, but we used 3D initialization like the radial one here, and then we re-implemented fully the projected gradient descent that alternates the gradient descent step and the projection step. So the gradient descent step is used to optimize the cost function, whereas the projection step is used to comply with the hardware constraints, both on the Gmax and on the slew rate simultaneously. And then you can end up with this kind of sparkling configuration in 3D, where a specific shot is highlighted in green color. And actually, we solve different numerical challenges to achieve this kind of results. Especially, we had to compute such kind of convolution between kernels and vectors, and for a large number of particle speed that represents the number of samples K-space. Of course, we used GPU implementation, but we used the PyKeops library, for instance, which was harmful because it limited the memory footprint. And alternatively, we also used fast multiple methods that utilize multiple expansion of the kernel psi here, allowing for a hierarchical grouping of closely related k-space spawns. Basically, this means that some k-space spawns, which are neighbors of each other, may be considered from a single source from a distant point. And this was really helpful to limit the computational burden here, where we have to manipulate like 10 millions of particles. And so we also solved a second challenge, which was related to the computational cost of the projection time. And we used GPU implementation as well. And as the number of shots was multiplied by a factor of 2, for instance, the GPU cost remains very limited in contrast to the linear increase of the usual CPU implementation. And then we did that, we implemented that and made use of the Joliot-Curie supercomputer. And once the trajectory was generated, they were implemented after discretization and derivation for getting the gradient waveform in the pulse sequence. So we compared first in simulation the performance and the behavior of the full 3D sparkling to the classical spherical strategy by computing the PSF. Basically, the PSF represents the quality of the sampling patterns. It's computed at the inverse Fourier transform, so it operates in the image domain. And as you can see here, on the 3 complementary planes, we got very better point spread function, so more concentrated, more focal peaks for the full 3D sparkling in comparison with the spherical approach. So less artifact along in particular in this coronal and sagittal planes. And this is also represented here by this reduction of the side lobes for the blue curve in comparison to the orange curve. Now, in terms of imaging, we collected some high-resolution data at 600 micrometer isotropic and the 3D Tesla scanner at Neurospin. And we took as reference image the classical 4-fold grappa accelerated, which basically amounts to 15 minutes of acquisition time. And then we compare different acceleration factor, 20, 40, and 70 for both strategies. And as you can see, the full 3D sparkling outperforms the stacking strategy at each and every acceleration factor. And we got a very significant, a very good image quality, even for the highly accelerated regimes. And based on these preliminary phantom results, we then moved to in vivo data acquisition. And here is an example of an individual, healthy volunteers at Neurospin, and we compared similarly the same strategy. And as you can see, we still got a reasonable image quality quantified by the structural similarity index, which basically varies between 0 and 1, and we got 0.94, which is very good in comparison to the poorest image quality with the spherical approach. So basically now we have a good 3D acquisition for isotropic high resolution T2 star rated imaging, both at 3T and 7 Tesla. But now in terms of image reconstruction, we have to face new challenges. Of course, for almost 4 years now, and based on the development of the COSMIC project, we have put all our developments in the PySAP software. So the PySAP is a Python package actually for sparse data analysis and image reconstruction. So it has been developed jointly with the Cosmostat team led by Jean-Luc Stark, and all the core developments were mainly based by Samuel Farrens on his side and Antoine Grigis on our side. And PySAP relies on 3 complementary pillars, one dedicated model for modular optimization, a second module related to availability of sparse decomposition like wavelet in 2D and 3D, and a set of plugins. And of course, in my group, we are developing the MRI plugins. And these MRI plugins actually is a very up-to-date compared to the state-of-the-art software package that implements various reconstruction techniques. So first, it is able to handle Cartesian and non-Cartesian data with GPU-accelerated Fourier operator. It works in 2D and 3D and with a single and multiple channel. And it also performs what we call either self-calibrating image reconstruction, in a case where you have to extract yourself and estimate yourself the sensitivity maps of the different channels, or calibration-less reconstruction, where instead of extracting the sensitivity maps first, actually you reconstruct as many images as the number of channels. This might be useful, especially if you want to get access to the phase information associated with this channel, with each channel. So here is a typical illustration of the different results. But for 3D image reconstruction, we actually realized that we need to go further. And so we decided to implement the density compensation operation. Basically, because we are doing non-Cartesian sampling with variable density, if you look at your data, your case-based data, and you perform a grading, if you compute the histograms, you will realize that, of course, the histograms follow the target sampling density and is not uniform. So the idea is that if you directly apply an inverse Fourier transform or a basic operation to get back to the image domain, you will end up some very severe artifact, because the high frequency will have a low weight in comparison with the low frequency. So for that reason, we implemented density compensation, which actually consists in estimating these histograms and inverting it, and introducing what we call a preconditioner in the computation of the gradient operator in the reconstruction formula. And by doing this, we can actually end up with a very good final image. And so we decided to evaluate the gain in terms of speed we can get using this strategy. And here is an illustration of the first iteration of our 3D image reconstruction algorithm. On the left-hand side with this density compensation mechanism. So we got this image with the 3 different and complementary views in 1 and 2 minutes, which is much better compared to the one we got without density compensation. And of course, this gives us the opportunity to perform online reconstruction directly on the scanner using the Gadgetron. This project was originally developed by Lubna El-Ghedari, my former PhD student, but it's now in the hands of Franck Monconduit. And at convergence, we can see that the density compensated allows you to get a much better SSIM score in a much shorter timing compared to the traditional FISTA reconstruction. So now we have seen how to speed up the acquisition. Now we would like also to see how we handle the usual susceptibility artifacts related to the B0 inhomogeneities. So susceptibility weighted imaging in particular relies on the T2 star weighted acquisition, and it operates a specific processing between the magnitude image and the phase image. So the raw phase image is filtered out to remove the low frequency, and then the 2 images are combined to actually emphasize and outline some typically the vessels and the high iron concentration that might be related to brain hemorrhage or microbleeds. So the problem is SWI imaging is that if we collect the data in presence of B0 inhomogeneities, this has a dramatic impact on the image quality. On top, on the right, it's an example of the application of a varying B0 on top of course, of the gradient in the readout direction. And as you can see, this transforms the image vertically. But because the readout is 1D here, the impact in the image is manageable. In the context of non-Cartesian acquisition, especially for sparkling trajectories, if you apply similar B0, then you end up with strong distortion, strong geometric distortion, and even some blurring. So now the question we want to address is how to correct for this kind of Earth resonance effects. And basically the corrections rely on leaving the classical Fourier model for image reconstruction and go to an extended Fourier model. And in this extended model, the classical Earth resonance or susceptibility weighted term is in red here. And omega is the resonance frequency offsets, which is caused by the B0 inhomogeneities. And this resonance frequency offsets is fluctuating, is varying with the position and time t. And usually, what we do is to collect a B0 feed map and then perform some post-processing to compensate for this feed map and reconstruct a good image quality. So in what we have done actually is slightly more ambitious, because this term, being a term that depends both on the frequency and the timing, can be actually approximated by an expansion which remains constant either in the frequency domain or in the time domain. So if you perform a frequency segmentation, then you end up with multiple image reconstruction that you can combine them, or instead, if you perform a temporal segmentation, then you will have to manipulate the shifted MRI data and reconstruct a single image in the end. And all what matters in terms of to approximate this term is actually the number of interpolators. And this is here on the right a representation of the influence of the number of interpolators that are used to approximate this exponential. Of course, as you can see, the larger the number of interpolators, the better the image quality. And now what we have tried to do is to perform this kind of correction without collecting a supplementary feed map. And this is a work, the PhD work conducted by Guillaume Daval-Frérot, so in collaboration with Alexandre Vigneault. So Guillaume is actually a CIFRE PhD student with Siemens. And we have realized that in the context of long echo time acquisition, the observed phase in the image can be decomposed as a sum of two terms, where we have the most significant terms depends both on the delta B0 fluctuation and on the echo time. And we have checked, of course, that the other contribution is quite negligible in our acquisition setup. Based on that, we can just approximate the B0 variation by this ratio directly from this equation. And so for doing so, we first reconstruct an image, then we separate its magnitude and its phase, which is wrapped, especially around the tissue interfaces. We apply unwrapping and then get an estimate of the field map. And this is exactly what is represented here on the bottom right, sorry, where we have a comparison of the feed map extracted either based on the collected data, supplementary collected data, or on the estimated one. And as you can see, both are very close to each other, especially the left column. The method associated with this technique is a much faithful compared to the acquisition. So that's why we use this technique in the following. And we reconstructed afterwards the images based on this delta B0 corrections. On the left-hand side, you can see that's 4 different slices corresponding to the 4 rows. The final image corrected using the delta B0 maps acquired separately or using the estimated delta B0 maps. And as you can see, both results are pretty consistent, but much better than not applying any correction. And of course, in the final susceptibility weighted image, the improvement is really significant because we combine information from the magnitude and information from the phase, especially in the region close to the nasal cavities, for instance, as shown by these small red arrows. And both approaches are very consistent. So by using an embedded delta zero map estimation, we saved, of course, the acquisition time of this supplementary delta B0 map, which is about a few minutes only, but which might be also prone to severe motion artifacts or so on. So to summarize here, so far I have presented to you the way we have optimized 3D sparkling that allows us to get a better PSF, especially along the Z dimension, and to show stronger robustness to higher acceleration regimes. Of course, we still need to introduce an instrumental target sampling density as input parameter to the algorithm. But basically, we were able to collect and reconstruct 600 micron resolution T2 star rated images at 3 Tesla in 1 to 2 minutes. In terms of image reconstruction, so whole solutions are developed in the PySap open source software. The multi-coil acquisition is supported. We have the possibility of accelerating the reconstructions thanks to the interface or support of the GPU NUFT and density compensation. And now we are also able to handle B0 inhomogeneities correction. But I would like to mention that this is quite computationally demanding because the last images I showed you took about 3 to 4 hours to get, to reconstruct. So now let's move to the second part of my presentation about the deep learning, because compressed sensing so far, so I've shown that we have a long reconstruction time. I also didn't insist on that, but the sparsity really depends on the choice of the sparsifying transform, and it requires also some hyperparameter settings. And all these aspects were mainly done by hand. So for that reason, we have also been working for now 1 year and a half on a deep learning solution for image reconstruction. And here is a summary of the whole possibilities of deep learning networks for MR image reconstruction. Some of them just start with basic image reconstruction and operate in the image domain only. Others operate in the sensor domain only, the K-space. Some of them, like AutoMap, for instance, estimates or fully parameterize through the network the Fourier transform, for instance. But in what we have decided to follow is a cross-domain learning that basically operate in both domain, K-space and image domain. So cross-domain learning is actually a technique that allows to alternate the correction between the image domain and the K-space by using appropriate deep neural networks. The tool actually is to enroll the classical optimization algorithms that are used in the variational setting. And here I show you a typical algorithm that alternates a correction in the K-space domain represented by the yellow block and a correction in the image domain represented by the application of the proximity operator of the regularization term, which is just a denoiser. And we can represent graphically this kind of mechanism by this sketch where the data and the known parameter are surrounded in red, the data consistency operation are in yellow, and one can pass from one domain to the other using the multi-channel Fourier transform, and the correction in the image domain are in blue. And now I'm going to present you the details about the algorithm we actually implemented. So we have actually unrolled the primal dual hybrid algorithm, which was originally proposed by Edler and a team in 2019. And except that we didn't really learn a specific network for the k-space domain. We just applied a residual correction. The reason why we did that is because it may seem at the first glance to apply some convolutional operation in the k-space domain, because convolution is supposed to operate a local transformation, but if you apply a convolution in the k-space domain, then it has an impact on the global image space. So that's why we decided to restrict to just convolutional neural network in the image domain. And then we also unrolled 25 iterations between the blue block in the k-space and the red blocks in the image space. And we used this kind of buffers that are very convenient to merge the consecutive iterates and optimize the convergence. And here on this sketch, of course, the T is supposed to be the multi-coil Fourier transform. With regards to the estimation of the sensitivity map, we actually follow the guidelines that was proposed by Sriram and colleagues this year because they win the 2019 FastMRI challenge last year. And so basically we apply a U-net where all the weights of the U-net are shared across the sensitivity maps. And now in terms of convolutional neural network for mimicking the denoiser, we actually replaced a classical U-net with an encoding part and a decoding part by a multi-scale wavelet convolutional neural networks. Basically, in this multi-scale wavelet CNN, the pooling is done using a simpler wavelet operator instead of making average pooling, for instance. And here we also omit the batch normalization because we use the batch size of 1. And we also limited ourselves to a less featured channel to make sure that the 25 iteration of the deep learning architectures fit in the memory of a single GPU. And based on that, we actually competed to the FastMRI challenge that I already presented some aspect during the Neurospin Science Festival. So it was a benchmark on brain MRI images. Compared to last year, the training set was really significant because consisting of almost 7,000 brain scans, approximately 40% were collected at 1.5 Tesla and the other at 3 Tesla. And the data set was rich also because composed of 4 complementary contrasts, T1, T2, T1 post after gadolinium injection and flare images. And all the data were of good quality because of the use of multi-coil acquisition. And we almost have 4,500 scans for the training set, with the vast majority of T2 imaging of T2 images in this set. We only participated to the 4x and 8x challenge, which means a 4-fold acceleration or 8-fold acceleration tracks. So here are the details of the training of our XPDNet. So XPDNet for primordial network, and X stands for the fact that we can use different kind of architectures. So the data was scaled. We use the classical random optimizer with default value for the learning rate. In total, we applied a number of steps of approximately 500,000 of because we used 100 epochs times the number of volume in the training set, which approximately corresponds to 1 week of training and GPU NVIDIA V100 for each acceleration track. The training was actually done separately for each acceleration track and then fine-tuned per contrast. We used the loss function, which corresponds to a compound of L1 on multiscale SSIM score, as advised in this paper, Ciuciu and colleagues, and the implementation is made open source. And for all this computation, we use the Janzi supercomputer. And here are some results on the validation for the four-fold track. On the left, the T1 contrast, then the T2, the flare, and the T1 post, with the ground truth at the top, our reconstruction in the middle, and the error at the bottom. And as you can see on the 4X track, the absolute error are pretty low and flat, so no structure. So which means that our reconstruction are very good and fair compared to the ground truth. And this is also outlined by the high PSNR score and SSIM score as well. And we also compared made some comparison between the XPDNet reconstruction and the GRAPPA reconstruction with our own implementation. So all this work was done by Zachary Ramsey. I forgot to mention that, I'm sorry. And we got very similar results in terms of image quality visually, but quantitatively, XPDNet outperforms GRAPPA, and also we got the solution much faster. Now for the 8X track, the image quality gets worse a bit because the PSNR and SSIM score decreased. And as you can see, particularly on the flare image, it's significant because we start getting some structures in the error, and this is also true for the T1 image. But when we compare to GRAPPA on this eightfold acceleration track, we can see that the XPDNet resists much better to this highly accelerated regime compared to the GRAPPA reconstruction, still with a very low computation time. So now we summarize the results, the quantitative results. So in terms of SSIM score, so on the challenge dataset itself, based on this, the SSIM metric, we were initially ranked third amongst 19 participants. And then, the people from Facebook only represented the first six track. And then the data of the finalists were submitted to radiologists for further evaluation using a Likert score, going from 1 corresponding to perfect image quality to 4 to the worst image quality. Earth Medical was still the winner of the challenge, so very consistent results between the radiologist and the SSIM score for both tracks. But then, during this evaluation stage, we got finally the second position, especially because we got a lower value in sharpness and artifacts. And interestingly, our colleagues from Facebook also performed some complementary analysis across the 6 radiologists that graded the images. So here we have 3 different representations. So Earth Medical was associated with the highest score, Neurospin with the lowest SSIM, and ATB with the middle. And as you can see, On the 4X track, we got the third position, but 2 times for 2 radiologists, but for the other, we got either the first one or the second one. And similarly for the 8-4 track. That's why we got the runner-up position in the end. And if you want, I forgot to mention, if you want more details about that, you can check out the keynote, the Fast MRI keynote, which is really insightful, and all details about each results, each criterion of evaluation are given. With respect to the qualitative evaluation of the challenge, so we can see that for the 4X track, all competitors reported very similar and consistent results, except maybe here for the T1 post-contrast, where we can see that our approach, as well as the one developed by ATB, reconstructed a false vessel, possibly due to some susceptibility effect that were introduced by surgical staples. For the 8X track, the results are worse, less accurate, because we observed, for instance, for the 3 teams, that we lose some very detailed information, especially in this T1 post. So to some extent, we smoothed out and we blurred the image quality. And here, we also smoothed out the details in the flare in comparison to the ground truth. But all competitors perform similarly on this kind of images. And now I would like to finish my presentation with 2 unpublished and unseen results so far. First, to show you the ability of XPDNet to transfer his architectures to new data, to unseen data, and I would say beyond unseen, to out of distribution data. So we got some very high resolution T2 weighted data collected at Neurospin and reconstructed on the left hand side with a GRAPPA algorithm. And on the right hand side, we just applied our XPDNet network, which was trained on different for a different acceleration factor at a lower resolution, and on data for which the cerebellum was not acquired. And as you can see, the reconstruction is very good. Especially, we were really able to reconstruct the details in the cerebellum, which was not completely expected, but it's really promising for the future. And last but not least, I would like also to show you that XPDNet also works for non-Cartesian sampling. Zachary has developed this extension recently, and this paper has been submitted to the conference IEEE ESB 2021. And in particular, on the original knee fast MRI dataset, he has applied a retrospective radial and spiral undersampling with a 4-fold acceleration. And he has also, with the help and the support of CEA-GR, implemented the density compensation mechanism. And on these different results, you can see the impact of the density compensation on the final image quality. So for the knee image and the difference image, of course, the best results being obtained with a combination of the PDNet with density compensation. And on top of that, you can realize that spiral imaging here, spiral undersampling, perform a bit better compared to a radial undersampling. So to summarize about XPDNet, so what I have tried to, I am try to convince you that deep learning is mature for MR image reconstruction, so in the supervised setting at least, because we got improved image quality at lower computational cost. We were also robust to various imaging contrast, signal-to-noise ratio, and field strengths. Of course, different network architectures were learned for the different acceleration track. And the Brain 2020 challenge was really hard compared to the previous one because no single coil track was made available. So only multi-coil data were proposed. So this was pretty demanding from in terms of memory and computation. Our solution was ranked first, so in this challenge, and first amongst the in academia. And the reason probably is that because it combines some physics-based knowledge and the recent advances in deep learning era. It also outperforms the GRAPPA algorithm at higher acceleration factors, and it's much faster. And it already works for non-Cartesian sampling. And it's 3D imaging, 3D extension, however, is in progress. It's not yet available. So in terms of perspective, we plan to work on the transfer learning also across the sampling schemes, across the resolution, and also across the contrast. Now to conclude, so in this presentation, so I have first talked about the shorter acquisition related to compressed sensing. So I showed you how we have extended the original 2D and stack of sparkling 3D to full 3D high resolution T2 star imaging that work both for 3D and 7T scanner at low spin. We hope that very soon this will also be available for fMRI, and see we are working with this in collaboration with Alexandre Vigneault in the context of Zainab Amor PhD thesis. And of course, the other imaging contrast still need to be tackled, as well as diffusion imaging. And we also plan to look at that with CEA GR. So in terms of image reconstruction, so our short-term goal is to also deploy this expedited solution for susceptibility-weighted imaging by embedding the B0 inhomogeneities correction in the deep learning structure, and this will be done by Guillaume Daval-Frérot. And so the deep learning, the 3D deep learning extension will be handled by Zachary, and it requires model parallelism using mesh TensorFlow, and we got some support from the developing team at Idris, Jean-Z. And then we also plan to transfer all the tools to other imaging techniques through collaboration at CEA, notably with Zineb Zaidi. In terms of perspective, we would like also, of course, envisage some functional imaging experiments for cognitive mapping. And of course, susceptibility-weighted imaging could be used for deep brain stimulation in the context of Alexandre Vigneault's project called the ANR Maniac, which has been resubmitted this month. And also for neonatal brain imaging, both for low field acquisition, so with Claude Fermont and his ANR very low field MRI, and also in the context of the project I submitted, Babar, to the last FedOpen call, and we plan to resubmit it to another call in the near future. With that, I would like to thank you for your attention, and of course, thanks all of my colleagues at CEA, but also at INRIA, and all the support, all the fundings coming from CEA and Siemens and the ANR team. Thank you.